Okay, today's speaker is Federico. Federico did his PhD in Ferrara. Then he moved to UBC here in Canada, spent some time in Oslo, and is now at the Universite Libre in Brussels. He's worked on, or he's working on both cosmic inflation and cosmic rays. And today he's going to tell us what the latter have to do with everyone's favorite topic, magnetic fields.
Okay, well, thank you very much. Thanks for the invitation. Okay, so what I want to talk about today is the latest results that we have with our collaboration, the Telescope Array collaboration, and the latest results that Telescope Array and Pierre, the other big observatory in cosmic rays, have been putting together as a result of the first collaboration between the two largest experiments in the field. Okay, so talk is divided into two parts. Part one, we'll discuss Telescope Array only, so the latest data from Telescope Array, and finally some very interesting results that we start seeing some anisotropy in the cosmic ray data, so what they call the hotspot. And in the second part, I will introduce this meta-analysis where we take Telescope Array and Pierre telescope observatory, and we put the data together. We'll find out how we can do that without biasing the data, and what we find in terms of the a full sky analysis, and analyze the effect of the galactic magnetic field on this analysis. So, okay, so I don't know what the level of cosmic rays expertise is here, so I'll start with our Japanese comic. So Telescope Array is collaboration between Japanese and Utah mostly. And so the Japanese distribute this comic in high schools to get people involved in the field, and so there's what are cosmic rays? So cosmic rays are particles that come from all directions in space at pretty much every possible energy you can think of. And so they hit the atmosphere, and as soon as they hit the atmosphere, they start disintegrating into smaller particles, and they create what is called a shower of secondary particles. So all these guys, which eventually make all their way down to the surface of the Earth, where we try and catch them. So cosmic rays are very energetic particles, and as professor here says, the individual particle has energies up to 1 billion electron volts. And in fact, this professor is a little behind with the current data sets, because if you look at the spectrum here, the 1 billion electron volt is down there. And we have now detected cosmic rays up to 10 to 20 and above electron volts. So 1 billion times, well, 100 billion times more than than 1 billion electron volts. And so what's shown here is also how hard is it to catch these cosmic rays? Because if you look at the highest energy, so what I'll be talking about today is from 10 to 18 and above, so the last tail of the spectrum. So at 10 to 18, you can catch 1 particle per square kilometer every year, which means that, and if you go further in energy, for example, 10 to 19, 10 to 20, you catch 1 particle per square kilometer per century, which means that either you have a lot of time to waste, or you have to build a big detector, okay? So that's why we built Telescope Array. So this is the status of current observatories for the highest end of the spectrum. So there's Telescope Array, which has been running since 2008 in the desert of Utah. Pierre Observatory, it's been running for 10 years in Malaga in Argentina. And the UHECR Array, the first real cosmic rays detector at high energies, that's been running for 40 years now. Okay, so Telescope Array. This is the collaboration. It's about 100 people. Like I said, it's mostly US and Japan, with a few people from Korea, a few people from the Russian Academy of Science, and me and my collaborator in Belgium. So it's a fairly small collaboration for the size of the experiment. So that's how Telescope Array looks like. So Salt Lake City is somewhere up there, about 3 hours, 4 hours drive. And so this is the layout of the surface detectors. So there's over 500 surface detectors that catch charged particles that cover about 700 square kilometers surface. They're spaced by a kilometer, they're on a grid on 1.2 kilometers. And these guys are overlooked by 3 fluorescence detectors, Black Rock Mesa, Long Ridge, and Middle Drum. And you can see kind of in the pictures here, so these guys house those fluorescence telescopes, so big mirrors that catch the light that comes from the shower. So this is how, the telescopes look like. So the mirrors, this is Middle Drum, this is Black Rock Mesa. And this is how they overlook the field of the surface detectors. Okay, so that's the concept of hybrid detector. It's very simple. So the cosmic ray hits the atmosphere, and it disintegrates, develops a shower. Eventually, these particles hit the Earth, and the surface detectors catch the charged particles. And at the same time, at night only, these guys are looking at the sky and trying to catch the light that comes from the same disintegration process. So by using all the information from hybrid events, you're trying to reconstruct the energy of these particles and the rather direction of these particles. So this is how an event looks like. From this is a triple event, so an event that's seen by all the stations. So the event hits somewhere on the surface, and this is the number of detectors that turn on and by how much. And then this is the trace that it leaves on the screens of the fluorescence detectors. Okay, so the data that we're talking about is the 6 years, the latest 6 years data. So the latest results are from 2008 to May this year. And so these are just technical details about how we choose the events. The important facts are, well, essentially the number of events. So we have about 3,500 events above 10 EeV, so this is 10 to 19 and above. And this number of events degrades down to 66 above 57 electron volt. And 57 is chosen because that's where we expect the cosmic ray spectrum to have a significant drop from cosmic rays at this energy hitting CMB photons and producing pions. So from this point on, cosmic rays start degrading in numbers. So, okay, so angular resolution is about 1.5 degrees and 20% energy resolution. Okay, so, now we have the data. So the question is, where do these guys come from? First question. And so one option is that these guys come from all directions with the same probability. So what you do is you run an isotropic Kolmogorov-Smirnov test to check whether an isotropic distribution is traced by a given number of points, which are your events on the sky. And you see that, for example, at 10, if you take the sample of 10 electron volt events, you choose, well, in some given coordinate system, since this is a one-dimensional test, you have to choose which direction you test. So if you test north to south or east to west, so right ascension or declination. And this is the probability that the events that you have are tracing the background distribution. The background distribution is isotropic. Probability that this is isotropic is as you see, it's pretty much 1. Okay, so it means that at low energies, we do not see any departure from a background isotropic distribution. However, when you look at the highest energy events, and these are the most interesting because they are the ones that propagate the least in distance, so they're the ones that see the structure the better, okay?
So you said that you expect to see like at 57.
Yeah, so from 57 and above, the spectrum has a sharp drop, but you still see some, but very few. Yeah, so it depends on what they are, which we don't know. If they are protons, 57 electron volts, they run for about 100 megaparsec.
Okay.
So pretty close.
So now you think that they're things emitted from like...
They should come from our neighboring clusters, for example. That's what you expect. And as you go at lower energies, they propagate longer, and the more they propagate, the smoother the distribution of matter is. So you expect to see less anisotropy. So, but of course, you have 60 of these guys and 2,500 of these guys. So of course, you trade in resolution for a number of events. Okay, but so after 6 years, finally, we saw this in the 5 years data, but it wasn't so pronounced. It seems that finally, for the first time, we're able to see some departure from isotropy. So for example, in this direction, so in declination, the probability that the cosmic rays that we see come from isotropic distribution in that direction is very low. So it's 0.5%. So we start really seeing that there is an anisotropy in the arrival direction of cosmic rays. So if they're not isotropic, second, the most immediate question is, okay, but then where do they come from? And well, the only reasonable answer is, well, they should trace the distribution of matter, because if these guys are accelerated at very high energies, well, they must be accelerated somewhere, and somewhere must be something, which means that we expect that large-scale structures of the universe should be sources of these cosmic rays. So the question is it true or is it not true? So what we do is you simulate the flux that you expect from large-scale structures. And the way you do it is you pick a galaxy catalog, and you take a galaxy catalog that follows the distribution of matter, and then you pick an injection spectrum. So you choose a spectrum of the source of cosmic rays. And then you propagate these cosmic rays from the galaxies to the Earth, and you account for all the possible interactions and the expansion of the universe. And then you smear the map of the flux, because you know that, well, the experimenter has not infinite resolution, and also we know the cosmic rays, every time they go through some magnetic fields, they are deflected. So we don't know exactly, we cannot trace the direction straight back where they came from, but there's unknown deflections that we have to account for, so we smear the map with a given angle. And then, okay, then you have an expected flux, and then you have all those points. You superimpose the points to the flux, and you see whether they are compatible or not. And this is how it looks like. So this is the field of view of telescope arrays, only northern sky. And each of these different colors, regions, contains 1/5 of the flux, which means that in each of those regions, you would expect to have 1/5 of the events that come from our data set. And so, okay, hotspot center is a bit of it's a spoiler for what I'll be talking about later. So for now, you see, so the white dots are the events, the highest energy events. And okay, so by eye, you can think you see something or nothing, but you can do an actual test. P-value is probability, chance probability. And you see that, so the green dots are for different smearing angles. You can smear more or less depending on what you think these particles are going to be deflected. And you see that the probability that the distribution of these points is the same as the distribution of the simulated flux is pretty close to 1 in the case the flux is built from galaxies. And it's very low, and this is another way to see the 0.005 that I showed earlier. It's very low if you, instead of a galaxy flux, you expect the flux to be isotropic. So the highest energy events at most smearing angles prefer to be tracing the distribution of matter and not to be tracing an isotropic distribution. So, okay, so now the hotspot. This is the, so last year we published, well, this year we published a paper from the 5 years data, from the data up to last year, where, so there seems to be a specific direction in the northern sky where most of the events seem to be coming from. Okay, so this you can see in these two maps. So what we did was, so if you look at this by eye, it looks like some excess of dots are coming from that side. Okay, so what we did, we oversampled the sky with a 20 degrees radius circle. So you take a 20 degrees radius circle, and then you go by 0.1 degrees, and you cover the whole sky, and you count the number of points in each circle every time. And then and this is the number of points in each circle. And you see that there is this region where number of points is much higher than ever else. Now, in order to understand whether this is significant or it's just by chance, you generate a distribution of events that is isotropic, which you call the background events, which is this distribution, which of course takes into account the fact that we're looking at this part of the sky much more than we're looking at this part of the sky. And then here you can do the same with this, and you count the number of events in the background distribution, which is isotropic, okay? And then you have a background number of events, and you have a detected number of events. And with these two numbers, you can build a significance map, which is what is shown here. So this is, in each point, depending on the color, is how many sigmas away you are from looking at this distribution from that distribution. And so the a priori, well, the pre-trial significance, you see that it goes up to 5 sigma. So in numbers, you can find the paper here. In numbers, we find a hotspot within a circle radius 20 degrees, centered at in this point in coordinates, with a 5.1 sigma excess significance. So now the point is,
excess over an isotropic distribution.
Over a background isotropic distribution. And so
basically the same statement that you made earlier, that the custom graded flux just isn't isotropic.
yeah, it's another way to say it. Now the point is to try and understand why it's not isotropic. Right. So this is one more way to try and understand. Okay, now we're looking for a specific direction where this is happening, right? So okay, so now, but this is a pre-trial. So in this case, we see by eye that there is an about 20 degrees circle excess somewhere, and so we need to pay the penalty factor that we looked for a specific location, and this was done by taking the same number of events. In this case, it's 72 events, and throw them isotropically in the sky 1,000,000 times. And each time we do the same analysis. So we have 72 events, but in this case, the 72 events are not the data events, but they're like Monte Carlo events. And then you do the same. You look around in the sky, and you try to find where is the maximum significance. And so you do this even for different angles in such a way that you you account for the fact that we guessed in the first place which angle we should have used. And this is the result. So this is the number of times. So this is the maximum significance. This is 5.1. And this is the million Monte Carlo set of events. And then we look at how many times in this million Monte Carlos you find a 5.1 sigma excess anywhere in the sky, so without specifying the direction. And this gives you the post-trial, so the penalty significance. So you count how many of these guys are on this side of the curve compared to that side of the curve, and it gives you, so this gives you a 3.4 sigma post-trial significance. Okay, so this is what with the data from last year. What happened with 1 more year of data? This is the same image, but now with 6 years of data. And then the number of events that fall into the hotspot goes from 19 to 23. And so as you can see here, and now most importantly, the significance map, it goes from 5.1 to 5.55, the pre-trial significance. So it seems that the more we accumulate data and the more these guys keep falling in the same place. And again, so pre-trial significance has upgraded from 5.1 to 5.55. Post-trial significance, so the same thing, but now you move this curve up to 5.55, and you count these guys, and it goes, so the chance that you end up in this part of the curve is 4 sigma, so it seems that we're accumulating evidence for this hotspot. We also ran a 1-year blind search, so we ignored the first 5 years of data. We just took the 6th year. So the first 5 years of data gave us the 5 sigma detection, if you want. Okay, now we know where to look. We know how to look, the 20-degree circle. We ignore all the previous data that told us that there is something there, like there is a source. And we just used the last year of data to see, well, if we didn't know there was a source, would there still be a source in just 1 year? Okay, so we ignore the first 5 years of data. And okay, we expect 0.94 events, we observe 3. So there's only a 7% chance probability that there is a hotspot with just 1 year of data. So it seems that the hotspot is building in the right direction. Now the point is, we don't know what lies behind it. Like I showed in the earlier map, there is really nothing special about this area. So the Ursa Major and Coma and Virgo, the big clusters are not right behind it.
How large is the circle again on that map compared with
well, 20 degrees would be, so like roughly half the size of this thing. So maybe
basically the circle would reach out to about the boundary of that.
it would be just about like the size of the first two colors.
So it's coincident with this void or whatever.
Yeah. So okay, so at this point, this is just what we found in the data. We don't have an explanation for why these guys should come from there. We know that there is a magnetic field that is shifting directions around, so we do not expect something to be right behind it. Sorry? Yes, the galactic magnetic field. Yeah.
And I'm sorry for coming in late, we had a meeting, but what's the expected dispersion in the magnetic field for this energy range?
For 57, it can be on the 10 to 15 degrees angle, which means that this guy would move pretty much, it could move up there, like could move anywhere within this box, but it couldn't move further out.
Size of the circle, in fact.
Yeah, it's about the size of a circle, yeah.
So wait, EEV is 10 to 18?
EV is at 18, yeah, 10 to 18. So we're talking about 60, 10 to 18. Yeah. Okay, so that's it. So we don't have a reason for this to be there, but we found it. Now we're trying to understand what it is. So this is so this is the first time at these energies in cosmic rays we find something that has such a a 5.1 over 5 sigma significance. So okay, so stay tuned for the interpretations, for the results. And okay, so let's take a couple of minutes break, and I will tell you a little trivia, like a true experimentalist, okay, which I am not, but experimentalists do it, so let's do it. So my first black widow. So when I was at the telescope this year, I saw my first live black widow. So one day I come back from the telescope, and there is this guy sitting maybe half a meter away from my pillow on the wall in my bedroom. And the black widow looks like this, more or less, a little smaller than that. So you see this red spot at the back. That is how I recognized it. And I knew it was not a good idea to be in the same room with this guy.
So did they give you a piece of paper when you first moved in saying, hey, this is what a black widow looks like?
Yeah, not really, but there is one at the university. There is the rattlesnake phone number and the spider's phone number, in case you find one in your room. But at that point, I didn't think about the phone number. So I saw this, but I swear when I saw it, I thought it was this.
Yeah.
So that's how I felt, okay? Is that, all right, but I won, so I'm here. So this guy is not there anymore.
You called
So-
the spiders?
No, I didn't call anybody. I just, I decided it was either her or me. So it was very quick.
Yes.
I just killed it. I killed it, I won. So I hope next time I find a black widow on my bed in Utah, it would more look like this one. Yeah. Okay, so enough fun. Let's go back to some serious physics. Okay, the story of two data sets. So for the first time last year, so telescope array is a detector that only looks at the northern hemisphere. And Pierre Auger is in Argentina, so they can see the other side of the sky. Okay. Now, for the first time, so last year, so for 2 years, we have been discussing about collaborating and putting together the data sets from the two experiments, especially after it became clear that Pierre Auger wouldn't have the money to build a northern observatory, and telescope array doesn't have the money to build the southern one. So,
What's the second experiment again?
Pierre Auger Observatory,
No, the second
telescope array,
telescope. What site? Where is that?
Utah.
Okay.
Yeah.
That's the update to the Flies Eye, or
Sorry?
that update to the
High res.
Eye?
Yeah, yeah. It's the same people, yeah. Okay, so at the ICRC, the Cosmic Rays Conference in Rio de Janeiro last year, the method was presented for the first time for the joint analysis. So finally, after a lot of politics, talks, and fights, we find a way to leave aside the hottest heads of the experiments and just actually do some work together. And so this method is now reality. So it's an actual data analysis that just appeared in the Astrophysical Journal. Okay, so let me tell you why we want to do it and what we do it, how we do it. So if you're looking for anisotropies on a sphere, one of the ways to look for a specific geometry of these anisotropies, for example, to learn where they come from, is to decompose your flux into spherical harmonics, just like we do in the CMB. So there are several reasons to be interested in particular in low multiples, but any multiple will carry information about the background distribution. And if the sources follow the large-scale structures, which is what we expect, large-scale structures have a distribution, a power spectrum in spherical harmonics, and then this power spectrum should be traced by cosmic rays if they come from the same place. Okay, so now why it's very important to have two experiments to work together. So if you only have half of the sky, okay, there is, besides a technical problem, which I'll tell you about in a minute, there is a there's a conceptual problem, because I can always cook up a distribution of cosmic rays, okay, or rather direction, a flux, that is extremely anisotropic, but it's isotropic in such a way that you only see the isotropic part of it. Because if you don't see half of the sky, the flux is all coming from the south, you see nothing in the north, and then you see it's perfectly isotropic, but it's actually 100% anisotropic. So some multiples cannot be determined, for example, a north to south dipole, or they can be determined with very, very poor accuracy. On top of that, when you reconstruct the flux from events, you have to invert if you have an infinite convolution matrix, okay, which is because you have in principle infinite multiples. Now, inverting infinite matrix is not possible, so you have to cut it somewhere. And depending on where you decide to cut this matrix, it will change the numbers that they come out of this analysis. Okay, so if you decide that nature just gave us up to L equals 3 multiples, and then you cut this matrix and look at how much is the dipole, how much is the quadrupole, they give you some numbers. But if you say, oh, I have up to L equals 12, and I look at the same numbers, well, even the dipole is different. Okay, now, which means that so whatever the results you get, they are unstable with respect to your assumptions on the flux that you have. So we don't want to assume anything about the flux. So we need to have full sky coverage, because if you have full sky coverage, then whatever the flux, you don't have to invert an infinite matrix, but you just use, in the formulas, you just use everywhere the 1 over exposure, which is now non-zero everywhere. Okay, so even if it's small, you just use the single value. So which means that we have to assume nothing, and even if it's very strongly inhomogeneous, this removes a lot of problems in the analysis. So okay, so now the point is, okay, now we want to put the two data sets together. How do we do it without screwing everything up? Okay, and so the idea is that since Auger sees up to this point in the sky and we see down to this point in the sky, there is a common band where both experiments see the same piece of the sky. So the point is, we know that the flux should be the same in this band, and we should see the same thing modulo the geometry of our field of view. Okay, so we decide to cross-calibrate the two experiments using this common band. So this is how the actual exposure looks like. This is Auger, and this is telescope array. You see, it's very inhomogeneous, but in this band, we see, both of us see the sky, the same sky. So how do we do that? So we have the nominal exposures, okay, which is how long the experiments have been running, which is the energy and the surface. And but nominal exposures, of course, since the experiments are calibrated in different ways, independent experiments, they're different machines because they have Cherenkov detectors, we have surface detectors. So you can never know the exact value that goes into, when you build the exposure for the full sky, you never know, because of systematic errors, what is the exact value that you have to use to rescale the two exposures in such a way that you get the right number. So how do we deal with this fudge factor that absorbs all the uncertainties that we cannot predict? So you see that, so so this is an example of how you could possibly do it wrong, okay? So if you ignore the fact that there is a fudge factor here and you just take one, so you just take the two exposures, put them together. Now, this is a simulated quadrupole, okay, with a given intensity. I think it's like 20% or something. And then this is how Auger would see it, okay? You see it's very pronounced. And this is how telescope array would see it. And you see it's much less pronounced. And the reason being that while we're smaller, we've been running for much shorter time, so we don't have as many events to trace the distribution as well as they do. Now, if you put these two together, you get a map that looks like this one. And this is not a quadrupole, okay? This is something that is not what you actually should see. So how do you fix this problem? Yeah.
So the bottom plot is a reconstruction of the flux after putting in this wrong reconstruction?
Well, it's just the sum of these two maps, just a plain sum, one top of the other one. So.
And these are some quadrupole multiplied with the exposure of the two individual instruments?
Yeah. So this is a quadrupole multiplied by exposure, yeah. by the individual exposure.
But then, I mean, isn't that fine when I expect to see something like the bottom plot? In the overlap region, I have the exposure from both experiments, so
Yeah. Yeah, but in the overlapping region, but these are nominal exposures. Again, the nominal exposure is uncertain. Like there is a systematic error that you cannot control. Now, we know that, I mean, b = 1 is a very bad guess, okay? We know that the relative exposure, I mean, we don't know this number with perfect accuracy, but we know that it's not 1, okay? It's 1/5 or something.
right. I guess my question is, if you knew the correct B, wouldn't it basically look the same?
No. If you knew the correct B, you would either upscale this map to make the quadruple more pronounced like this one, and then when you put them together, it just looks like a quadruple, or you would downscale this map in such a way that you smoothen it in a way that it looks exactly identical to the northern one, and then it becomes a quadruple again. But the point is that in this process of going from this resolution, if you want, to this resolution, there is an uncertainty that you cannot control.
Well, for a given area of sky, the exposure must be latitude or zenith dependent.
Yeah. It's geometry dependent, yes.
So,
But this part is easy. I mean, the geometry is known because it's, I mean, we know.
okay, so the issue, though, so that's known quite accurately.
Yes, it's accuracy, and also the issue is because exposure depends on your energy, nominal energy, okay? Because you have to decide how many events you accept in your data set. And this depends on where you cut the set. And where you cut the set depends on where your absolute energy scale is. And now our energy scale and Auger energy scale, we know that they are different. They differ by at least 15%. So we know that there is an uncertainty, and either they decide that they're wrong, or we decide that we're wrong, or we find a way to deal with it without telling where this error comes from. Okay?
Can you describe differences in the calibration method for the two experiments? Because that's so important historically.
Yeah, well, there's this, essentially because the main difference is that in telescope array we use Monte Carlo calibration for the energy, and also because we have different detectors. Okay, we have surface detectors that are scintillators, and they have Cherenkov tanks, and so yeah, so there are like the ways the events hit on the surface, and the way, yeah, and we reconstruct with Monte Carlo simulations for the showers, and they I don't remember exactly what's the procedure for their reconstruction method, but.
But wait, now Auger both directly detects the shower particles.
Yeah. Auger is also hybrid. Yeah. Auger is also hybrid.
Okay, so you're both hybrid experiments.
Yes, but the surface detectors are different.
But the surface detectors are different.
Yes, and the procedure for energy calibration is also different. And in any case, so you can, yeah. So there's about a 15 to 20% overall energy shift in the spectra that we see. Okay, so this is, like I said, this is how you on purpose make it very wrong. Okay, we know that this number is about 1/5, but the point is that 1/5 is not good enough because we're trying to detect anisotropies that are of the order of few percent. Okay, so we need something better. Okay, so how you do it is, well, this number, in principle, you can actually calculate because, like I said, we have the common band, and in the common band, the flux is the same. Okay, now in the common band, you can calculate this number because exposure is, by definition, this formula. Okay, the geometrical exposure is something that, again, you know because it's just geometry, and then the uncertainty in the energy calibration is just the number of events that you count. But now, well, we know how many events we have, we know how many events they have in the band, so these numbers are also known, okay? So this number of events for Auger, number of events for us. So if the only unknown thing in this formula is the flux. But now, if you make a first assumption that the flux is isotropic, then this guy goes outside of the integral, this guy goes outside of the integral, and they simplify, okay? And we know that the flux is almost isotropic, so it's a good assumption. Now you have a first guess on what B is, and this is how the sky looks like with the first guess, and it's much better than the previous one, okay? So, I mean, there's still something here, but it's much smoother, and you see that this has become more pronounced, and so this gives you a map. Now you have a map, you get your spherical harmonics out of the map. So you get a first set of spherical harmonics. Now you have a first set of spherical harmonics, and then you can reconstruct the flux, okay? And then you can put a second guess on the flux, so you do it again, and then in this case here, the flux is the first spherical harmonics reconstruction of the flux. And okay, then you get a different B. you use the different V and you look at the map, and all of a sudden this looks much better, right?
Although in practice, there must be some fluctuations in delta n.
Yes, so there is. So the fluctuations in delta n.
Is the square root of delta n fluctuation in the actual number of events?
Yes, so that will give you the error. That will give you the error on the multiples that you extract, and this is indeed what we do. So you get this fudge factor, and you iterate. Okay, you do this bootstrap technique, and after a few iterations, you find that the ALM you get and the B are stable. And in practice, so we tried this in a lot of simulations. This converges after very few steps because the flux is very close to isotropic. Okay, so we've never had to run our code for more than 4 steps or 5. Now, okay, so we do this, and again, you do the same with Monte Carlo simulations, and that's how you get the errors, because in Monte Carlo events, the delta, so the number of events in the band changes at each simulation, and this is how you get the errors out, and these are the results. So this is how the events look like for the full sky. So for the first time, we have a map of the sky with cosmic rays all over the place. This is the TA events and the Auger events, and these are the numbers. So here, okay, you don't have to look at all this. Like, this is just to show that the errors and what we get. So the important thing to see here is that, again, you see that the error on the north to south dipole is much larger than the error on the other directions. Okay, so east-west and right and left, or whatever you want to call it, and also you see this propagates in higher multiples. Okay, so the north to south direction is always the most poorly determined because it's where the coverage is the most inhomogeneous. So the question is, okay, is there any anisotropy here? So this is a color-coded significance table for all the ALM. So this is M and this is L, and this is how many sigmas they're away from isotropic, which is 0. Okay, so isotropy, we expect all of them to be 0. And you see that some of these guys are maybe like 3 sigma away. The question is any of these guys actually significantly away from it? And then you can take all these significances and put them on the A over sigma curve. And the black line is a normal distribution, and this is the histogram of these colors essentially. And so we see that there is nothing in this map that is standing out from isotropic distribution.
Is this the same energy range that you showed before? The 57?
It's this, this is 10 is electron volt. Yeah, so I should have mentioned that. So this is with 10 is electron volt. And the reason we do it to 10 is electron volt, because if you want to do cost calibration with the band is only a very small fraction of the sky, and it's also the fraction of the sky that both experiments see with the smallest exposure, because it's the end of our field of view. Which means that if we do it with 57, we have 3 and they have 7, and it's not good. So we need more statistics. Okay. Of course, we want to do this for higher statistics, for higher energies, but at the moment we cannot do it. So, okay, so like we expected, also this analysis doesn't show any departure from isotropy at lower energy. Now, the question is, okay, but what do we expect from structure? Okay, so this is what we expect from structure. So this is the power spectrum now. So it's not ALM single ALM, but it's the sum, square sum of the ALM, so the power spectrum. And so the data are the orange points with the errors, and blue, red, and blue, green, and red are the simulations. So this is the spherical harmonics obtained from the flux map that I generated, the same flux map that you saw earlier with the different gray bands, okay, the areas. So the same identical map, smoothed with different Gaussian smearing. And this is the expectation. So you see that, okay, so higher multiples, the errors are big, we cannot really say much. But you see that, okay, there is a tendency for these guys to be lower, but the guy that really stands out here is the quadruple, okay? So to go from this point in steps of this error bar all the way up to the 15 degrees smearing, it's really far away. So it seems that there is some maybe, so this is yet one more way to see how a structure is not reproduced by our events. And we do this way also because we want to try and understand why it is so. Okay, so now we have some maybe information about the geometry of this discrepancy. So we may say, okay, maybe if we find a reason for this quadrupole to be low, because maybe, for example, the magnetic field of a galaxy or some systematic effect, then we may be able to understand why we don't see the structure as we expect them to see.
I'm sorry, what does the data exactly mean here in this plot?
What is the data? Well, this is the...
Theta.
Sorry?
The angle.
Angle.
Oh, theta, the smearing angle for the flux map. So when we simulate a map, we smear it with a given angle, and this is how wide is the smearing. Okay, so the most obvious explanation for why this quadrupole is missing is that, well, you blame it on the galactic magnetic field, because that's the first thing you can think of. Also because the galaxy looks like a pancake, a quadrupole looks like a pancake.
So the ab initio calculation you've done, just to be absolutely clear, you have the exponential attenuation of the cosmic rays, the interaction with the CMB, and then you downweight the contributions of large-scale structure from larger and larger radii by basically an exponential attenuation factor, or?
Yeah. So you just propagate these cosmic rays and account for all the energy losses, including expansion of the universe, and then you see. But of course, one of the assumptions is you have to know what they are. And so all our maps, because telescope array is the composition analysis of telescope array prefers protons at all energies. So all our simulations are run with protons, which is exactly the opposite of what Auger does. Okay.
So you don't see any evidence for the...
We don't see any hardening. We don't see any heavier at higher energies. So our simulations are run for protons, but in principle, one can run for whatever. Okay. So this is all with proton primaries.
But just, okay, I'm sorry, so you have a certain energy that you're looking at. Now, only the highest energy cosmic rays are downscattering by the interaction with the CMB.
Yeah, only at 50, yeah, yes.
So clearly the lower energy cosmic rays, or the lower energy part of the energy bin, is going to be sensitive to large-scale structure in a different way than the higher.
Yes, that's correct. Yeah.
And, but you're basically throwing it all together because you have limits.
Yeah, you just choose a lower bound in the energy, and then you propagate everything from each energy and above, and you look at the resulting flux.
Larger than 57 EeV.
Yeah, so in the harmonic analysis, everything larger than 10, and in hotspot analysis is 57.
I see. Thank you.
For statistics reasons. Yeah. Okay, so why do we have a missing quadrupole? So is this the galactic magnetic field? And the first, so I don't have time to go into models of the galactic magnetic field. There's several. These are the two models that are most commonly used for the regular component, the coherent structure of the magnetic field of the galaxy, which typically consists of a disk plus a big halo. And then on top of that, you put some smaller structure, randomly oriented field, which you can find the details of in these papers. Just to have an idea, a feeling of what the galactic field does to cosmic rays, this is a simulation taken from this last paper that came out this September. It's a simulation of how much cosmic rays at 60 electron volts are deflected when they get to the Earth. So this is how. So you see that towards the galactic center, there's like up to 15 degrees deflection for protons. Okay, because of course, if these are heavier particles, then the whole thing is much more, and it will be all red. And so this is how much they are deflected. And then on top of that, this is the regular component. And on top of that, you have a variance that comes from these deflections, because we don't know the orientation of the small scale structure. And this is how much the variance is for the same model. So it's up to 3 degrees towards the center of the galaxy, down to about a degree around. So this is what you expect for the highest energy protons. Of course, 10 electron volt protons will have the same deflections times 6. Okay. So what does this magnetic field do to the spherical harmonics? So the first question is, can we trust the power spectrum? So if we throw in the magnetic field, or we don't throw in the magnetic field, what happens to the power spectrum that we expect from the simulation? And this is what happens. So this is ALM. So this is L, and this is the azimuth number. And these are the CL. And the colors and the numbers in the boxes tell you how much the values of ALM and CL, so the power spectrum values and the spherical harmonics value, move around when you change the strength of the magnetic field. So in this case, we started from 0 magnetic field, and we went up to twice as much field as the best fit model, okay, with a given model. And then we look at how much the ALM and the CL change in value, okay? And you see that while the power spectrum coefficients, this is percent, okay? So the power spectrum coefficients don't seem to be particularly interested in what's happening with the magnetic field, okay? So they go off by 20%, 30%, but they stay more or less in the same place. Whereas because these guys are direction dependent, okay? So they know about the direction you're looking at. Some of these, they lose their power completely in favor of some other ALM, especially at higher. So this, what the whole thing this is telling us is that the direction-dependent coefficients are not reliable when you're looking at something propagating through the magnetic field, but the power spectrum is not going to change much whether you do have a magnetic field or you don't, okay, at this energy. So now that we know we can trust the power spectrum, we know that we need to isotropize this quadrupole. So we know that the galactic magnetic field is not responsible for it. So we know that we want to isotropize this power spectrum, and so we can, for example, throw in heavier particles together with protons. And this is how, so this is what we do here. This is the smearing angle again, so it accounts for unknown deflections for the random field. And this is the fraction of iron from 0 to 1 that we throw in our primaries. So now we don't propagate only protons, but we propagate protons plus iron with a different weight, okay? And the colors here tell you how many sigmas away you are. So it's essentially the distance from the points of my, of here. So the distance between, at a given angle, the distance between this point and this point. Now, but the simulation is not only protons, the simulation is protons plus iron. And okay, so you see that without the galactic magnetic field, you need to introduce maybe 20% iron to be within 2 sigma away from the actual data set. So it's nothing dramatic for the dipole component. So this is the first multiple. There is a slight preference for more isotropic sky, but it's not so pronounced. And if you throw in the galactic magnetic field tends to isotropize a little bit, so you go 1 further sigma closer to the actual data. But the more important one is, well, the quadrupole again, of course, because we saw that the uncertainty is small and the distance is much larger. So the Chinese electron volt data have very low p-value, very low probability to be tracing structure at small angles, and we see this in the quadrupole very pronouncedly, because here we're 6 sigmas away from a quadrupole that is what the data is telling us, okay? So this is telling you that you need at least half of your primaries should be iron, or there should be some way to isotropize these guys up to 50% of the total flux in order to reconcile the data with a simulation. And again, you turn on the galactic magnetic field and things go a little better, but again, you just move everything down by a factor of 1 sigma. So the quadrupole seems to be the main contribution to this tension between the large-scale structure simulation and the data. Okay, so the data is telling us that there is no structure in a quadrupole where we want to see it, because the simulation is.
Just said the prediction of the quadrupole amplitude was done using galaxies, or using AGN, or.
It's the galactic. It's a galaxy catalog, so it traces the matter distribution. Well, of course, one can choose a catalog of something else, and but of course, it will not be much different because AGNs pretty much stay where. So there could be a bias, but again, when you look at this picture, this is 6 sigmas away. It's a lot.
Well, you use AGN, it will be more anisotropic, not.
It will be more exactly. Okay, so yeah.
One more question. Switching on the galactic magnetic field here means you.
Which model is it?
Whatever best fit amplitude.
Which model?
The 2 models.
It's the Shirkov and Tiniakov-Kronberger.
I guess you've checked that as well.
But you can do with either, yeah.
What do models say about the magnetic field in the galactic halo?
Do you mean the strength of the field or the shape of the field?
Any assumptions about that? Because you obviously don't really know it.
Well, I mean, for the model, you have to make an assumption. You have to decide a function that you fit with some numbers, okay?
Yes,
And so it's a toroidal field that has a Gaussian.
In practice, those models don't give a significant bending from a large-scale Hale magnetic field.
Well, if you just look straight up north and south, no. But up to 30 degrees from the galactic plane, it's quite significant. Yeah, so I mean, I showed you what it is, this guy.
Sure.
So that's how much super high energy protons are deflected, okay? So around here, this is 10 to 15, and of course, if you just look up this way, it's next to nothing.
This magnetic field model is basically developed from galactic synchrotron bands.
This particular one is developed is from synchrotron and from rotation measures. But yeah, so this is the latest one that came out in there. But in our code, so this is with the Surkov model, but in our code, I mean, it's just a matter of which function you put in as a magnetic field. So we do it also with other models, and the results are more or less the same. Okay, so conclusions, part one. We didn't expect anything. Well, that's not completely true, but we found something. So we didn't expect anything because like for years we didn't see anything, but we found something. So what did we find? So in telescope array, only looking at the northern sky, after 6 years of data, we seem to, so the highest energy data shows some incompatibility with isotropic distribution, and there is a strong evidence now for a hotspot where events seem to cluster. There's nothing special behind it, so we don't know what could be. We know that the magnetic field will move this guy around, but magnetic field models tell you different things about where this hotspot should be moving. So we do not either trust the magnetic field model or they need to be more refined.
Is OJ able to observe that spot on the sky?
Sorry? No, because they look at the opposite side.
Okay.
They don't see this part. So we have some new data, some interesting results that we need to think about. So then part two, we did expect something, but we found nothing. And this is, so finally TA and Roger have been collaborating for putting together a full sky map of cosmic rays. And we developed a very robust and unbiased way to reconstruct the spectrum. The harmonic analysis is compatible with isotropy, but we know the structures want to see some more isotropic skies. And we do not see it, especially low multiples, especially the quadruple. And the galactic field, we just realized, well, we tried to fix it with the galactic field, and we didn't fix it, so it doesn't work. So there must be something else that isotropizes up to half of the total flux that comes from the sky, which could be higher composition or something else, exotic mechanisms or something. We don't know, so that's everything. Thank you very much.
Can you say a little bit more about this new extended telescope array?
The low energy.
It's low energy.
It's low energy, yeah. So it's called TAIL, Telescope Array Low Energy, and it's built and it's taking data now ever since. But actually, real data that we're going to use for analysis only for the last couple of months. So we started taking data when I was there last time, and so it's designed to catch particles from around 10 to 16.5 to 10 to 18.5. So it's going to bridge the spectrum that we have now from 10 to 18 and above with the known spectrum from the lower energy. And the reason this is very important, well, the most important reason that we can think of is that because energy calibration is very difficult at higher energies. So, for example, telescope array has a given nominal energy. Pierre has a different nominal energy. There's a shift by 15-20%. And so if we're able to, with a single machine, to connect the spectrum that we know where the absolute energy is to the highest tail, then we fix the energy once and forever. And then once you fix the energy once and forever, you have also a lot of information about what the composition is. Because then once you fix the energy, you see where the ZZK cutoff is, we see where the ankle is, and then you can pinpoint this energy are protons or this energy are ions. So then,
what specifically will you be able to do with composition on this? Because this is an energy range where composition should be changing significantly, right?
Well, the point is, okay, so in terms of composition analysis by itself, it doesn't matter whether you have tail or not, because we're looking at different energies, okay? But tail will tell you where the beginning of the highest energy spectrum is, in which exact point, and then you fit your spectrum with the power law, okay? And where this broken power law is broken depends on the composition of these particles. Okay, so the ankle and the GZK cutoff, they're not independent on composition. So the GZK cutoff is at 57 if it's protons, but it's shifted if it's iron. And the same for the ankle that is at 10 to 18 and a half, okay? So by fixing the energy, then you automatically know at which energy this dip is and the GZK cutoff is, and so you can infer information about composition. Yeah, so that's, Auger is also building let's say a lower energy extension. So we'll also have complementary information from them. Actually, Auger just deployed, I think, 6 of their tanks into the telescope array site, so that we're going to start observing some events with the same, and running our Monte Carlo with their own tanks in such a way that we can understand the difference in energy and the difference in composition and reconstruction. But yeah, so.
A little bit more just as background about how the ability to measure composition depends on energy. I mean, what are the different constraints at 10 to the 16 versus 10 to the 18 or 10 to the 19?
Well, you mean how? So you mean how the?
Well, you measure the composition apart from the development of the aircraft.
You measure it from the depth of the shower. So the depth of before the shower. Heavier particles travel like protons travel much more than okay. And the point is that because you can only reconstruct the depth of the shower from the fluorescent detectors, which are only on at night when there is no clouds and the weather is nice. Then you have it's really hard. I mean, you really have very few events to reconstruct it, and also from that point on, you have to use hadronic simulations to follow the distribution, the development of the shower, like the shape of the shower. And hadronic simulations have really huge errors. Okay, well they don't claim to have errors, but every time there is an update, for example, LHC just updated complete constants and form factors and PDFs and so on and so forth, and all of these simulations just shifted by 10-20%. So that's why the composition is so hard to make. And at the highest energies, well, it's really hard because, well, we don't have events. And, well, we don't have events, and the hadronic simulations are the most uncertain because the higher energies, and the more you have to extrapolate from what we know from particle accelerators to get to that simulation, right?
Will this recalibration by the LHC affect the claims made by Auger about the increasing weight or the possibility of the increasing weight of the particles with energy?
Well, which means we can't.
Is it increasing or decreasing?
Auger observes heavier composition at highest energies, right, and we observe the same composition at all energies.
But will this recalibration you're mentioning from the LHC affect that?
Well, in our case, it doesn't change much. In their case, they still see heavier elements, but instead of going all the way up to iron, now the best fit is a combination of protons, helium, and nitrogen with different percentages. So yeah, this latest update after LHC has pushed down their composition, but still it's not protons. Like still they see, so like this curve that gives you the depth of the shower given function of the energy. In our case, it stays flat, and in their case, it just goes down towards higher composition, just not as much as before.
LHC is hardly given the last word on this stuff. So.
Yeah, it's not, no. But again, LHC goes up to some energy, and then we go 6 orders of magnitude more. And then, okay, then you have to take a simulation and extrapolate, and hope that everything goes well.
I have one more question about the hotspot.
Yeah.
So you showed in the second part of your talk that the magnetic field basically isotropizes everything. there any way how you,
It isotropizes a bit.
is there any way how you could build a contrived magnetic field model that focuses and gives you a task?
I mean, if you ignore the data, rotation measures, probably, yeah.
Right, but you would say that's rule out.
No, but the point is, yeah, so but the point is, so the magnetic field, yeah, so but the isotropization that happens, like the difference between this and this, so 1 sigma, is for 10 east electron volts. Now, if you go a factor 6 energies higher, deflections are factor 6 lower. So if you throw in the magnetic field or not for 60 east electron volts, then this thing would change very little. So the hotspot just stays more or less where it is. I mean, okay, within 10 degrees. And then, so yeah.
All right, let's move upstairs where there are cookies, I think.
Okay.